Hi, good day everyone. So these are some examples of sound and hearing. Problem 1. In a sinusoidal sound wave of moderate loudness, the maximum pressure variations are about 3.0 times 10 to the minus 2 pascals above and below atmospheric pressure. Question is find the corresponding maximum displacement if the frequency is about 1000 Hertz. We have to take note that at normal atmospheric pressure, the speed of sound in air is 344 meters per second and the bulk modulus is around 1.42 times 10 to the 5 pascals. So what are we going to find is the maximum displacement given is that the maximum pressure variation, I call this one as Pmax, is equal to 3.0 times 10 to the minus 2 pascal. By the way, we will also call this one Pmax as pressure amplitude. Okay, pressure amplitude. So question is, we're going to solve for the maximum displacement. Maximum displacement is just the displacement amplitude A. So what is A? We know that the relationship between Pmax and A is given by this. Pmax is equal to the bulk modulus times the wave number k times the amplitude A. So from this one, we can solve for the displacement amplitude or the maximum displacement. This is equal to Pmax over the bulk modulus times the wave number k. We know bulk modulus. The bulk modulus is equal to 1.42 times 10 to the 5, but we don't know the wave number k. But we can solve k, so it can be solved from this expression. K is equal to the angular frequency over the speed, v. Speed of sound, v is equal to 344. The speed of sound, v is equal to 344 meters per second. So this is my bulk modulus, okay? And omega, in terms of frequency, this is equal to 2 pi f, okay? So omega is just equal to 2 pi f, and f is equal to 1000 hertz. So we have 2 pi f over v. So this is equal to 2 pi times the f equals 1000 hertz over the speed of sound. This is 344 meters per second. So therefore the wave number is equal to 18.3 rad per meter. So we know now the wave number k, we also know Pmax, so this check, the bulk modulus is also given, k is 18.3, so now we can solve for the amplitude. Amplitude is equal to Pmax 3.0 times 10 to the minus 2 pascals over the bulk modulus, which is equal to 1.42 times 10 to the 5 pascals times 18.3 rad per meter. So the maximum displacement or the displacement amplitude is equal to 1.2 times 10 to the minus 8 meters. Okay, so this is now the maximum displacement when the frequency is around 1000 hertz. Okay, next problem. Sound waves in air has a frequency 1000 hertz, a displacement amplitude of 1.2 times 10 to the minus 8 meters, produces pressure amplitude of 3 times 10 to the minus 2 pascals. Question is, what is the wavelength of this wave? For a 1000 waves in air, what displacement amplitude would be needed for the pressure amplitude to be at the pain threshold, which is equal to 30 pascals? And we note that the speed of sound is 344 meters per second, and the bulk modulus is 42 times 10 to the 5 pascals. So for question A, what is lambda? And we can solve for lambda. It is just equal to V over F, where V is equal to 344 and frequency is 1000. Then we can solve for lambda. And for letter B, we will solve for the displacement amplitude. So displacement amplitude is just the A. What is A? If Pmax is given, which is equal to 30 pascals. Okay, so we will solve for lambda and we will solve for A. So lambda So solution, letter A, lambda is just equal to V over F, and this is equal to 344 meters per second over the frequency equal to 1000 hertz. So lambda, the wavelength is equal to 0.344 meters. For letter B, we need to solve for the displacement amplitude A, and displacement amplitude A is just equal to Pmax over bulk modulus times K, and this is equal to 30 pascals. The Pmax is equal to 30 pascals, and the bulk modulus is 1.42 times 10 to the 5 pascals. Multiply this by K, where K is unknown, but we can solve for K from this 2 pi f over the speed of sound. And I think we solved this one for a 1000 hertz. Okay, for a 1000 hertz, this is 344 meters per second. We solve for K in problem 1. We solve for K, this is equal to 18.3 rad per meter. So this is equal to 18.3 rad per meter. Using calculator, 30 over 1.42 times 10 to the 5 times 18.3. The displacement amplitude is equal to 1.15 times 10 to the minus 5 meters. Okay, so for the next problem, a ship uses a sonar system to detect underwater objects, as shown in the figure. The system emits underwater sound waves and measures the time interval for the reflected wave or echo to return the detector to the detector. Determine the speed of sound waves in water and find the wavelength of a 262 hertz wave. Okay, so there are two unknowns here. First is we need to determine the speed of sound in water. Okay, and we will find the wavelength of a certain frequency of this of the sound wave. So first we need to solve for V, and then we need to solve for the wavelength lambda. Okay, so in order to solve for the speed of sound in water, we will use the equation for the speed of sound in liquid. And the speed of sound in liquid is equal to this square root of the bulk modulus over the density of the liquid, in which in this problem the liquid is this water. So for the speed for the bulk modulus of water, this is given. Okay, for water, B is equal to 2.18 times 10 to the 9 pascals, and the rho, the density of water, is equal to 1000 kilogram per meter cube. Okay, so now we can solve for the speed of sound in water. This is equal to bulk modulus, which is equal to 2.18 times 10 to the 9 pascals over the density of water, 1000 kilograms per meter cube. So this is around 1480 meters per second. So this is now the speed of sound in water. Take note, if you compare it to the speed of sound in air, the speed of sound in air is around 340 to 350 meters per second. So it is much faster than in air. The speed of sound is much faster in water compared to in air. Okay, so the speed of sound in water is around 1480 meters per second. So once we solve for the V, we can solve for the lambda, because lambda is just equal to V over F, where V in water is equal to 1480 meters per second, and the frequency of that wave is around 262 hertz. So therefore the lambda is equal to 5.65 meters. So the wavelength of this wave is around 5.65 meters. Okay. Next, compute the speed of sound sound waves in air at room temperature. Say at room temperature, the temperature is around 20 degrees Celsius, and find the range of wavelength in air to which the human air, okay, the audible range, okay, the audible range is around 20 hertz up to 20,000 hertz. We have to take note that M, the mean molar mass for air, is given, which is equal to 28.8 times 10 to the minus 3, and the ratio of heat capacity is gamma, okay, in air is 1.40. Okay, so we need to solve for the V in air. We have to take note in air, V is the speed of sound in air is dependent on temperature. Okay, so V given is that the temperature is around 20 degrees Celsius. We can now solve for V, and this is equal to this expression gamma R T over the molar mass M. Gamma for air is 1.40. R is the gas constant equal to 8.314. Okay, 8.314 joule per mole Kelvin. And the temperature is 20 degrees Celsius. And take note, we have to take note, you need to convert it to Kelvin. 20 degrees Celsius is around 293 Kelvin. Okay, so therefore, V is equal to gamma, which is equal to 1.40 times R, which is 8.314 joule per mole Kelvin, times the temperature, which is equal to 293 Kelvin, divided by the molar mass, which is equal to 28.8 times 10 to the minus 3 kilogram per mole. Okay, per mole. So using calculator, that is 1.4 times 8.314 times 293 over 28.8 times 10 to the minus 3. Take the square root. The V now is around 344 meters per second. The next question is find the range of wavelengths from 20 hertz to 20,000 hertz. So if F is 20 hertz, okay, then lambda is equal to V over F, which is equal to 344 meters per second over F 20 hertz. So this is around 17.2 meters. For F equals 20,000 hertz, then lambda is equal to V over F, which is equal to 344 meters per second over 20,000 hertz. This is equal to 0.0172 meters, or around 1.72 centimeters. Okay, so the range of wavelengths is from 17.2 down to 1.72 centimeters. Okay, for audible range of 20 to 20,000 hertz. Okay, next problem. We have find the intensity of the sound wave with the maximum pressure amplitude, which is equal to 3.2 times 10 to the minus 2 pascals. Assume that the temperature is 20 degrees Celsius, so that the density of air is equal to 1.20 kilogram per meter cube, and the speed of sound is 344 meters per second. So what we need to find is the intensity. And intensity can be expressed in terms of this equation in terms of Pmax, which is equal to Pmax squared over 2 times the density times the speed of sound. Okay, so therefore Pmax is equal to 3.2 times 10 to the minus 2 pascals quantity squared divided by 2 times the density of air, which is equal to 1.20 kilogram per meter cube, times the speed of sound, which is equal to 344 meters per second, Therefore, the intensity of this sound wave is around 1.24 times 10 to the minus 6 watt per meter square. Now, if we wish to convert this to decibel scale, okay, so the intensity equal to 1.24 times 10 to the minus 6 watts per meter square is equal to what in decibel scale? We know that beta is equal to this 10 decibel times the logarithm of the intensity over the reference intensity I naught, where take note I naught is equal to 10 to the minus 12 watts per meter square. So in terms of decibel, that intensity is equal to this log of I is equal to 1.24 times 10 to the minus 6 watt per meter square divided by 1 times 10 to the minus 12 watt per meter square. Then this intensity in beta or in decibel scale is equal to 61 decibel. Okay, so that intensity 1.24 times 10 to the minus 6 watts per meter square is equal to this 61 decibel in decibel scale. For our next problem, for an outdoor concert, we want the sound intensity to be 1 watt per meter square at a distance of 20 meters from the speaker array. If the sound intensity is uniform in all directions, what is the required acoustic power output of the array? So in this problem, we use the definition of intensity as power per unit area. And what we need to solve here is the power output of the array, in which it is denoted by P. So P now is equal to the intensity times the area, where I, or the intensity, is given equal to 1 watt per meter square. Now the area in question is a hemisphere centered on the speaker array. So if this is our speaker, okay, and then the intensity of this a sphere, we have to take note that the surface area of a sphere is equal to 4 pi r square, but the area in question here is only half of the surface area of a sphere, because this one here is our ground. Okay, this is our ground, and we assume that none of the acoustic power is directed into the ground. So therefore, the area that we're going to find is only this one. So the area of a hemisphere, and this is just equal to 1/2 of 4 pi r square, where r is equal to 20 meters. So we have area is equal to 1/2 of the surface area of a sphere, and I is equal to 1 watt per meter square. So this is actually equal to 2 pi r square. So therefore, power is equal to IA, and this is equal to 1 watt per meter square times the area, which is equal to 2 pi, and R is given by 20 meters quantity square. So therefore, power is around 2.5 kilowatts, or this is 2,500 watts. So the required power output of the array is around 2,500 watts. Okay. Next problem. A 10-minute exposure to 120 decibel sound will typically shift your threshold of hearing at 1000 Hz from 0 decibel up to 28 decibel for a while. 10 years of exposure to 92 decibel sound will cause a permanent shift up to 28 decibel. Question: what intensities correspond to 28 decibel and 92 decibel? So what we need is to convert 28 decibel into intensities and 92 decibel into intensities. We have this formula from decibel to intensity. We have I is equal to intensity naught times 10 raised to the power of beta over 10 decibel, okay, where I naught is equal to 10 to the minus 12 watts per meter square. So when beta is equal to 28 decibel, then the intensity I is equal to this. We have 10 to the minus 12 watts per meter square times 10 raised to the power of beta. Your beta here is 28 decibel over 10 decibel. Okay, so we have 10 to the minus 12 times 10 to the 2.8. 28 over 10 is 2.8. So therefore, intensity here when beta is equal to 28 decibel, this is equal to 6.3 times 10 to the minus 10 watts per meter square. So 28 decibel is equal to 6.3 times 10 to the minus 10 watts per meter square. Now when beta is equal to 92 decibel, then the intensity I is equal to this 10 to the minus 12 times 10 to the 92 over 10. Okay, 92 over 10, this is watts per meter square. So I, when beta is 92 decibel, is equal to 1.6 times 10 to the minus 3 watts per meter square. So 28 decibel is equal to 6.3 times 10 to the minus 10. 92 decibel is equal to 1.6 times 10 to the minus 3 watt per meter square. Okay, problem number 9. A locomotive traveling at 35 meters per second emits a whistle of frequency 800 Hz. Question, what is the wavelength of the sound waves in front and behind the locomotive? So basically, we will need to find the lambda front and the lambda behind. Okay, lambda front, what is lambda front and what is lambda behind? Okay, so for lambda front, we have this equation where v is the speed of sound, vs is the speed of the locomotive, where fs is the frequency emitted by this locomotive. So plug in the given, where we assume that the speed of sound is 344 meters per second, vs is 35, and frequency is 800 Hz. Therefore, lambda front, wavelength front in front, is equal to 0.386. For lambda behind, or lambda back, it is equal to v plus, okay, for behind, that is plus vs. Plug in the given, we have 344 plus 35 over 800, we will get 0.474 meters. Okay, next, problem 10. Same locomotive traveling at 35 meters per second, which emits a whistle note of 800 Hz. Question is, find the frequency heard by the listener if the listener is stationary and in front of the locomotive. So when we draw this one, this is our locomotive, the source of the frequency, and it is moving towards the stationary listener. Okay, since your source is in front, the listener is in front of the locomotive, it means that the source or the locomotive is moving towards the listener. Where the listener is stationary, so VL is 0, VS is minus because your source is going towards the listener. So therefore, the frequency heard by the listener can be reduced into this one. Plug in the given, where VS is 35 and FS is 800. Then the frequency heard by the listener is around 890.61 Hertz. So take note, it is greater than the frequency emitted by the source, since your source is moving towards the listener. Okay. Next is, what if the listener is stationary and behind the locomotive? What is the frequency heard by the by the listener. So when we say behind the locomotive, your source is this one moving away from the listener. Okay, your source is moving away from the listener, where VL is also equal to 0 because listener is stationary, and Vs is moving away from the listener. It means that your Vs is a plus, uh, it's a positive number. So therefore, the frequency heard by the listener can be reduced into this one, and plug in the given, we will get frequency heard by the listener is around 726, which is less than the frequency emitted the the source, because your source is moving away from the listener. Okay, next, same locomotive traveling at 35 emits a whistle note of 800 hertz. What is the frequency heard by the listener who is now moving and approaching the locomotive at 20 meters per second? So the listener now is not stationary, but it is moving, and it is the motion is towards the locomotive. So when we draw this one, your source is this, okay, and then the listener is also approaching the locomotive. So the VL is plus, VS is minus. So therefore, the frequency heard by the listener is equal to this equation. Okay, uh, VL is positive while the VS is negative. Plug in the given, where 20 meters per second is your VL, and then your 35 meters per second is our VS. So therefore, the frequency heard is around 942.39 hertz. Next, find the frequency heard by the listener who is receding the locomotive at 20 meters per second. Receding means that the listener is moving away from the source or from the locomotive. So they are your source is also moving away from the listener, and the listener is also moving away from the source. So from that, Vs is plus, Vl is minus. So the frequency heard by the listener is equal to this equation. Plug in the given, you will get 683.90 hertz. So that's the frequency heard by the listener. So you have to take note the sign convention of our VL and VS. Okay, and I think that will be all. Thank you for listening.